All right, let's go ahead and get started. Once again, thank you guys all for coming out. I know it's been a really stressful week with midterms and the election and all that. So appreciate you guys taking some time out of your busy schedule to spend an hour or two with us. So today we'll just be building off of some of the concepts we've gone over in the last weeks. We've talked about building different kind of models and how to evaluate them, and we'll be going over two or three depending on how our time looks. We'll be going over two or three different new models today, and we'll just be going over at a high level what exactly they are and how exactly we can implement them. So that'll be decision trees, that'll be random forest, and if we have time, we'll get into k-nearest neighbors as well. Awesome. So let's jump right into the code today. No slides today. So just hop onto that link and just the usual chain of events. Just download it, go to Colab, and then upload it so that you have your own copy that you can edit and follow along in. So we'll give everybody about a minute or two to do that. If you're new, Varun's going over the steps in the video, so you can just follow exactly what he's doing. And let me know if you're unable to download or you don't have access to it or something like that. We'll look into that if that's an issue.
So just like always, go download the file, open up Colab.
Can we get the link in chat? Yes, you can. It is, yep. It is tinyurl.com/apply_ml4, just like that. Hey Dan, thanks for jumping in. We're actually just about to get started, so I just dropped a link in the chat. It's tinyurl.com/apply_ml4. That is the link to our Colab notebook, and if you could just download that and then re-upload it to your Google Colab, and you should be good to go there. All right, and has everybody gotten a chance to, actually, let me phrase that differently. Is there anybody that hasn't uploaded their own copy to Google Colab yet? Can you just drop something in the chat just so we can maybe wait another 30 seconds? Okay, we'll hold on for about a minute, no worries. And as always, let us know if you run into any issues. All right. Anybody still having issues with uploading the Colab notebook? Going once. Going twice. All right. Looks like we're good to go. Cool. So in that case, let's go ahead and get started. So like I said, the first thing we're going to be covering today is a decision tree. I think decision trees are pretty advantageous because intuitively, they're probably the easiest ML algorithm to understand. Essentially, in decision trees, what we're doing is we're asking a bunch of questions to get to our answer. So, let's just do a quick example of that. So, let's say you had to guess the name of a celebrity and, you're allowed to ask as many questions as you want, right? Kind of like a game of 21 questions. So start off with a very broad question. Are they male? I'll tell you the answer is yes. Are they currently an actor? Answer is no. Are they from the USA? No. Do they have a beard? Yes. Are they a musician? Yes. Are they a singer? Yes. So am I a big fan of them? Yes. So hopefully all of these clues kind of help you narrow down to who I'm talking about any guesses, just drop a guess in the chat if you have any idea who this person could be. All right. Well, Varun, if you could just run that chunk of code for me, and it should tell you exactly who it is. And there's a picture of the greatest artist of the 2010s. That's my boy Drizzy Drake. And to all the haters out there, yes, Drake can sing. So, how does this apply to ML, right? So, essentially, like, there's a few patterns I want you to take away from that exercise we just did. You know, you notice that we first start off with a pool, like a very big pool of potential celebrities to start off, right? Then the question is, are they a male? So that cuts the pool, more or less in half. And then we get even more specific. Are they currently an actor? No. Are they from the USA? No. So every question kind of narrows you down all the way, narrows you down like more and more and more till at the end, you're only left with a few possible answers to choose from. So that's essentially at a very high level what we're trying to do, in a decision tree. So we ask a series of questions, and then we follow some sort of criteria to get to our answer. So Varun, if you could run the next chunk of code for me, that should show a photo of what exactly decision tree would look like. So let's say we have a decision tree that we are trying to use in order to buy some sort of car, right? So this image shows you an example of what a decision tree like that would look like. So we start off with our baseline assumption that like of color. So is color red, right? If the color is red, we go to the left. If the color is red, we go to. If the color isn't red, we go to the right. Then we ask, is the color yellow? No. If it's not yellow, then we don't buy it. If the color is yellow but it's a Ferrari, then we do buy it. On the other side of the tree, you see if it's a model that's newer than 2010, we automatically buy it. If it's not newer than 2010, but it does have more than 50k kilometers if it does have less than 50k kilometers of mileage, we do buy it. So essentially, what the decision tree is doing is it's giving us a kind of a path in a tree-like structure, where at every node in the tree we make some sort of decision on which way in the path to go. Then once we get to the bottom of the tree, we have a decision on whether or not to do a specific action, or in our machine learning case, which classification we would give a certain example. So yeah, overall idea of a decision tree is we essentially ask a bunch of questions, follow a certain criteria, and then at the end try to classify the um, we try to classify our feature, or excuse me, our example, based on the different features we have and based on the answers we have to those different questions. So now instead of maybe buying a car, guessing a celebrity, let's try to apply this to something we've been working on over the last few weeks, and that is the Titanic data set. So let's say I let you ask enough questions about a particular person on the Titanic. Do you think that if you were able to ask a certain number of questions, you'd be able to guess whether or not that person survived? If we asked the correct questions, the chances are that we would probably be able to, guess whether or not they survived. Like, if we know, just, calling back to our first workshop, if we know that they're a male and they had a ticket in the third class, then they're probably not very likely to survive. But we know that, if they're a female but they had a ticket in the highest class, they are pretty likely to survive. So that's kind of the series of questions that we'll be asking in our decision tree. And scikit-learn has a fantastic library that lets you make decision trees using just one or two lines of code. So let's go ahead and code up the decision tree and see how it does. So Varun has the code right here. We're just going to start off by importing our data. We made it nice and easy to avoid any of the headaches that we had in that second workshop. And yep, as you can see, this is pretty much our standard data. And then now we're gonna go ahead and split our data into the train and testing groups. And yep, so we have our labels and our features first, and then after that we get the train and test. And just to check that our train and test split actually worked, it's always good to check what's happening in your code. In that next chunk of code, we essentially just sum up the length of the x train and the x test, and then that should be equal to our overall Titanic data dot shape. And you see that 889 matches up with the other 889, meaning our train and test split worked exactly how expected. All right. So now that we have all those formalities out of the way, we can get into actually making our decision tree.
Before that, do you get quickly drop a 1 to 5 in the chat if you feel like you have a decent understanding of what a decision tree is like and um, like why it's useful. And also let us know if you have any questions at this point.
Okay, seen a 4, seen another 4, 4.7. Thanks, Jacob. All right, seeing a lot of 4s. That's good to hear. And yeah, like Varun said, if at any time you have any questions, just feel free to either interrupt or just drop it in the chat, and we'll get to that. So this code here should look really familiar to you guys. This is pretty much the exact same format we've been following for our logistic regression, for our neural network. This is the nice thing about scikit-learn is that all of this is really standardized. You import your tree as a decision tree classifier, and then you fit it to your X train and your Y train, and then all of a sudden you have your model. So Varun, if you could run that to train our model for us really quick. Awesome. So let's take a look at some of the parameters here we have in our decision tree classifier, right? So I want to point out one thing, which is the criteria. That's in our case, that's Genie. So the criterion is essentially, telling your decision tree how it's going to ask the questions and in which way it's going to ask the questions at a very high level. Max depth tells you how many questions your decision tree is allowed to ask. Max number of leaf nodes is how many leaf nodes can you have in that tree of your decision tree. And of course, random state at the bottom, very useful just for testing. So just like a neural network, there's a ton of different hyperparameters here in our decision tree that we can tune to try and adjust its performance. But of course, before adjusting its performance, it's good to get a baseline of how our decision tree currently is doing. So just quick exercise, if you guys could print the training accuracy of our decision tree and print the testing accuracy of our decision tree, just to get a baseline understanding of how we're doing. And it should be in the exact same format, very similar commands to what we've been doing in previous workshops. So give you guys about a minute or two to do that one. All right, I think it's been about a minute. Anybody have any answers on how to do this? Just feel free to drop it in the chat. Should be very similar to what we've done in the past. Tree.model.score X train Y train. Oscar's got it right on the dot. Good work, Oscar. That should be for our training accuracy. And then for our testing accuracy, very similar to what Oscar has put in, except just change the X train to an X test and change the Y train to a Y test, and we should be good to go. So initially, before we run the testing accuracy block of code, we see that our training accuracy is really, really high, right? 98.4%. That is awesome. If we can always have a model that runs 98.4%, that's pretty much exactly what we need. But if we print the testing accuracy, Vern, if you could do that for me real quick, we see that it drops all the way to 74%. So, what's happened here? It seems like our decision tree model did great on our training test, our training set, got 98% accuracy, but all of a sudden when we go to our testing set, we drop to 74% accuracy. It's just cratering, right? So we're going to be answering the question of why this happens in just a few minutes here. But let's see like what exactly our model is doing. So one thing that's nice about scikit-learn is that there's all of these libraries and functions to really support everything you do in ML, and then kind of support the sort of side visualization things you do in ML as well. So earlier on when we had that car buying decision tree, we had the full visualization of exactly what was going on in a decision tree, right? We could see like what questions we were asking. We could see like we're choosing my color, we're choosing my mileage, we're choosing my make. But it'd be nice to see what our scikit-learn decision tree is doing when it's trying to decide whether or not somebody survived in the Titanic data set or not, right? So if we run this chunk of code here, Varun, if you could run that for me, this should show us exactly what is happening in our tree and what our tree looks like. So that should probably take a minute. It's a bit of slow. It's kind of slow to generate that whole image, I suppose. Okay, whoa. So just looking at this, our decision tree looks massive, right? Like it's not even fitting in our screen. It looks like there's more than like 10 plus layers in our decision tree, at least 50 plus nodes. Our decision tree is massive. It's so big that we can't even see like what the text is in the boxes, right? So we have a term for this. So when this decision tree is like really large and sprawling, and you see that huge gap in training and testing accuracy, uh, that is called overfitting. Does anybody have any idea, just off the top of their head, what overfitting is and what it means? Just feel free to shout it out or just drop it in the chat.
Isn't it basically when your training data is good, like you get like a nice score,
Right.
but then the testing data, it's not as accurate, probably because you were too specific when specifying hyperparameters for the training set?
Yep, that's exactly right. I think Cameron also has another definition in the chat. We say when you learn the data instead of the patterns. Yep, that's also true. Uh, so overfitting is essentially, you can essentially identify it when you're doing really well on the training set and doing really badly on the testing set. Because what's happening is your decision tree or your model is learning the specifics of your training data and is not able to learn the general trends in your training data. You know, uh, your model is essentially memorizing, your training data, but it's not able to generalize to the testing data. Oftentimes, this is because the model learns the noise in the data instead of actually learning the real patterns that we're trying to show it. So, does anybody have any ideas on what we can do to maybe reduce the overfitting in our decision tree and try to get that testing and training accuracy to be closer to each other?
Before we get into that, I feel like it's helpful to get an intuitive understanding of what overfitting could look like. So, my go-to example for something like this is, let's say you're setting two people up on a blind date, and you want to help your friend identify the other person in the restaurant. So, it's probably going to be helpful to tell your friend, okay, the person you're going to be meeting is roughly 6 feet tall, has black hair, wears glasses, and so on. It's probably not going to be as helpful to tell that person, okay, this person was wearing a blue t-shirt last week, is probably wearing a watch with a brown strap, is probably wearing, I don't know, gray shoes or whatever. Because that information can change, and it's not going to be necessarily helpful if you're trying to figure out who that person is in the restaurant. That person may no longer be wearing the same clothes, but that person is always going to have some features that are the same. So in any decision tree, you want to capture those important features and ask the important questions, and not worry yourself too much with trivial questions or trivial features of the data that can change. So that's what overfitting essentially is. You don't want to memorize what that person was wearing on a particular day. You want to basically convey the information. This is how the person broadly looks, and this is how you can identify them. So that's the difference between really understanding, like creating a model that understands the patterns in the data as opposed to just memorizing the data.
Yep. I just dropped a link in the chat that links to an image that I think does a nice job of explaining overfitting. Probably should have just put this into the notebook itself, but if everybody could just open up that image real quick, you can see like on the left side of the image, we have something that's underfitted, right? Where it's not learning the data whatsoever. In the middle, you have a good fit where we're not learning specifics of the data points themselves, but we are able to learn, the general trend of the data. And on the right side, you have overfitted, where we're not learning the general trend of the data. We're just looking at like specific data points and trying to get like perfect predictions on every single data point rather than generalizing to the data itself. So yeah, we should probably stop here for questions actually. Are there any questions about overfitting? And just 1 through 5 in the chat, if you guys could drop a number in. How are you guys feeling about your understanding about overfitting right now? Cool. Seeing some 4s and 5s. Glad to hear that one's making sense. Awesome. So second question then, how do you guys think we can reduce our overfitting in the specific decision tree model itself? Any ideas? Less and broader questions. That's one idea. Yep. I think that pretty much encompasses the approach to reducing overfitting as a whole, where you're trying to make your model broader. And yeah, for our specific decision tree case, that's pretty much exactly what we want to do. We want to limit the questions we're asking and make sure the questions we're asking are broader questions, right? So let's take a look at this next chunk of code here. And what we're going to do right here is restrict the number of questions our model is able to ask. If you guys remember from earlier, I was talking about the different parameters that the decision tree model had. And one of the ones I pointed out was max depth. And max depth controls the depth of the tree and pretty much puts a limit on the number of questions your tree can ask, right? So Varun, if you run that chunk of code for me, you see, so here is our decision tree now. So let's take a look at exactly what's happening in our decision tree. So Varun, if you could just scroll to the top really quick of that image. Okay, so in this first node here, we're taking a look at x1. If x1 is less than 0.5, we go to the left. If it's greater than 0.5, we go to the right. I believe x1 is x1 the gender column? Not exactly sure. Let me look that up.
Yeah, I think it's the sex because cabin class is the first one.
Right. Yeah, and then we keep going down the tree. Yep, we keep going down the tree. On the right side, we look at, or excuse me, on the left side, we look at if x5 is less than 26.269. I think x5 is age, if I have that correctly. So if somebody is younger than 26.269, we go to the left. If not, we go to the right. So you can kind of see what the decision tree is doing here, right? It's kind of breaking down our data and then kind of making a decision on whether to go left or to go right. So if you look at the last line in each box, so value equals 379 and 93. That's on the top left box on the screen here. So what this is doing is it's saying that on the left side of this tree, we have 379 values. On the right side of this tree, we have 93 values. On the other side, if you look at the top right box, value equals 61 and 178. That means on the left side of the tree, we have 61 values. And then on the right side of the tree, we have 178 values. So this is pretty useful for seeing like, okay, how important is this question I'm asking? Is it really getting me a good split? That first question we ask, we see that it divides our data by 1/3 and 2/3, which is a great question, right? That first question you ask should be really broad and like eliminate a lot of the possibilities that you have. You don't want to ask a really specific question in your first decision tree question, right? You don't want to ask something like, is this person above the age of 93 and a male and you don't want to ask all these things at once, right? You want to ask a very broad question that lets you quickly narrow down your options and then in the end converge on a singular option. So Vern, if you scroll all the way down to this, all the way down in this picture, we see that, you know, at the bottom, these are the predictions we're making, right? And you know that samples will tell you exactly how many predictions end up there. And yeah, so you can see that some of these boxes did quite well. Like if we look at the box all the way to the right, we can see that it predicted 21 in one class and 2 in the other class. That means this box is doing quite well, right? It's really helping us make a concrete decision on whether or not it's somebody survived or somebody died. Then you have boxes that aren't so good, like the one that's second from the right with a Genie value of 0.475 with a value of 35 and 55. You know, that's a lot closer to, you know, a 40-60 split. So that's not as good of an answer that our decision tree is giving us. So if we look at the accuracy and the test accuracy and the training accuracy of our decision tree, I think that was like right above right. So although our training accuracy dropped a little bit, our test accuracy jumped a ton. It went up by, I think, like 7 or 8%, right? So this is a lot closer to what we want, because we want our training accuracy and our testing accuracy to be very close to each other, because that tells us that our model is able to see the generic trends in the data set and is not overfitting. Question from Advite in the chat: will the order of levels of the decision tree always be in the same order of the columns in the data set? No, it will not. So we're going to go into, I think just in a minute, we're going to talk about how the decision tree decides, you know, what questions to ask and which way to go. But good question though. Can we quickly go over the bottom boxes again? Yes, absolutely. So let's take a look at the boxes on the bottom again, right? So once we've reached the bottom of the decision tree, that means we have no more questions to ask, which means that we have to make a decision based on the information we have. So some of the boxes are going to be quote unquote like really good boxes, which allow us to make really clear decisions. For example, if we look at the box on the bottom right, where value is equal to 21, 2. What this means is that if somebody reaches this box, of all the data points that reach this box, 21 of them survive and 2 of them die. So what does this tell us? That if we do end up reaching this box, it's like a 90% likelihood that this person survives, right? So this means this is a good box because it really clearly allows us to make our decision on whether or not somebody survived or died. Then we can look at the box that's second from the left with value equal to 35, 55. So that means if somebody reached this box, 35 of them survived and 55 of them died. So that tells us we have about a 40-60 split between people surviving and dying if they reach this box. That means this box really isn't that great. It doesn't give us a whole lot of information, right? It gives us like a 40-60 split of actually being correct, which is pretty close to a 50-50 random guess. Cameron, does that make sense? Does that answer your question? If not, what questions do you have? And, you know, how can I help you understand something?
Yeah, that's good. Wait, doesn't that bottom box not add up with the split given in the box right above it? Like it has 90 samples, but didn't the top one say it only got 56?
Let me clarify that. So what's happening here is that let's say you have 113 samples. What the value tells you is out of those 113, how many of them belong to the first class and how many of them belong to the second class. So the number of samples is going to add up to this because some of them are the people who survived, some of them are the people who didn't. And then out of these 113 samples, it's going to split it again into 2 questions. And the first question, so the answer is yes, it leads to 90 samples here. And if the answer is no, it leads to 23 samples over here. So this 90 plus 23 is going to give you this 113 over here. So for any node in your decision tree, what you should always have is the sum of the values should be equal to the samples. And for any output over here, the samples over here, 90 plus 23, should always give you the number of samples in the previous layer. You can see that holds pretty consistently over here as well. So 54 plus 72 is going to give you 126. And in this box, you have 121 belonging to one class and 5 belonging to the other. So the ideal situation is that you want to have a fair number of samples but you also want the value to be highly distorted. So you want very few of one class and a lot of the other class so that you can make a clear prediction. So yeah, if you look at the tree, ideally, so when you start off, you have 440 people who didn't survive and 271 people who did. Uh, as you go down the decision tree, you'll see that the ratio keeps improving. So now suddenly you have in both these nodes over here, you have 379 to 93 and 61 to 178. And the idea is that as you go down the decision tree, you in some sense reduce the entropy of your data. So you basically want to make sure that each node is relatively uniform in the classes of the data point that reach that node. And that's how that's essentially how the decision tree picks which questions to ask. Basically the ones that reduce the entropy of uh, the model. So we have a question here. How exactly is the Gini score calculated? It doesn't seem to be a simple proportion. You're right. So it the Gini coefficient is not exactly a simple proportion. Uh, what it is, like I mentioned before, is an indicator of the entropy in the data. For people who took chem, uh, it's roughly the same idea. You want to essentially reduce the chaos in your data. So in any particular node, if you have many people who survived and many people who didn't, that's quite confusing. You don't really know whether to predict yes or no for any given person. That's a high entropy. That's known with a high entropy value. So the Gini coefficient is high. So after you ask a single question, what you want to do is divide it into two nodes where the ratio of yes to no is a lot higher or smaller. And in this case, the entropy of the data reduces because you have fewer members of one particular class. And so you can see that the Gini coefficient reduces. So from 0.472, it becomes 0.316 and 0.38. And that trend holds as you keep going down the tree. So as you keep reducing the chaos in your data, uh, you're asking better and better questions.
Yep. We've kind of abstracted away some of the more complicated math with the decision tree, but like Varun is saying, essentially we're asking a question at every node where what with that allows us to gain the most information out of our data. It's a concept called information gain, and information gain is directly related to entropy, like Varun said, where we're trying to reduce the uncertainty in the predictions we're making. Advite asking, so since our decision tree chooses those questions with the least entropy, does that mean that when we specify max depth equals 3, our decision tree automatically consists of the 3 questions that give us the most clear answer? I'm not 100% sure, Advite. Maybe Varun has a better answer for you, but from my understanding, it's more of a greedy algorithm where at every stage it will look to reduce the entropy the most, and then it'll ask a question there, and then the next question it asks will try to reduce the entropy even more. So it's not like it makes a list of all the possible questions and then cycles through them to see which ones lead to the best answers. It's more of a greedy algorithm where like at every step we try to ask the best question that we can.
Yeah. So like Harsh mentioned, if you look at this tree over here, and then you look at the massive tree that we got before, if you cut off this massive tree at depth 3, it's going to look the exact same as this particular tree.
Right. Does that answer your question, Kyle and Advait?
Yeah, thank you.
Awesome. Good to hear. Cool. So let's try a different approach now. So first, our approach was limiting the max depth. So now let's try giving the decision tree a little bit more information on how exactly to split, right? So like we're saying, an interesting parameter is to look at that Genie value provided in every box. So I guess in the notebook, I've put a very high level definition of what the Genie impurity value is. It essentially tells us the probability that a sample would be misclassified if we randomly assigned a label at that point. So essentially at a very high level, it's telling us how important the decision we're making is, right? So the higher the Genie value, the more clarity that specific question is going to give us. So, all right, quick discussion question. Would it be better to remove a branch with a Genie of 0.5, or would it be better to remove a branch with a Genie of 0.05? If we're trying to reduce overfitting, which branch would be better to remove? Right. And so Advite says branch with 0.05, and why is that?
Because the larger the Genie value, the higher the likelihood of misclassification. So the more of a general question, I guess, it encompasses.
Exactly. Yep, exactly. That's exactly what we were looking for. So we can tell our model to stop asking questions if we reach a very small Genie value for a certain node. And that's actually exactly what we're gonna go ahead and do here. So Varun, if you could run that for us. Okay, so looks like we reached that smaller Genie value pretty quickly, and we can see that right there. We kind of stop asking questions. So if we just take a quick look at our model here, it doesn't look like it's done great because the values are like pretty evenly distributed in some of the ending boxes, like the value equals 67 and 47, or value equals 35 and 55. So the model hasn't done great. In fact, the accuracy of the training data and the test data dropped by a percent or two. I think we're around like 80 or 81% now. So, maybe this wasn't the best approach to take. But of course, there's a lot of different approaches in ML, and I think we're going to try one more right below. So another way is to set a minimum number of samples needed at a box in order for it to be split further, right? So let's say we get to a box where samples equals 3, but our distribution is like value equals 2 comma 1, right? If we continue to ask questions there, that's very, very specific. That now we're getting into like overfitting type territory where we're likely only splitting on something that's very specific to this data set and not actually looking for a higher level trend like we should be. So we're gonna let you guys do this one. Try implementing a decision tree with a limit on the number of samples, and you guys go ahead and decide on your own what that number of samples should be, and then drop your training and test accuracy in that chat, and we'll give you guys about actually 2 minutes is probably a little bit low. Give you guys about like three or 4 minutes to do that, and then let's see who can get the highest training and highest testing accuracy here. Awesome. So we'll give you guys a couple minutes to do that. And yeah, if you have any questions in the meantime, drop us a note in the chat, or feel free to come off mute and ask your question.
The code should be pretty similar to what we had above over here.
And once you guys create the model, make sure to print it out as well, like print out the tree so we can visualize the entire tree and see exactly what it's doing. Awesome. So I think it's been about 2 minutes. How are you guys doing? Do we need a little more time for this one, or should we move forward? Cool. We'll wait another minute or two. No worries. What is the max underscore leaf underscore nodes? I think max leaf nodes should just say like what is the max number of nodes you're allowed to have in your decision tree, I think.
It's basically the ones that it's max leaf nodes is exactly what it sounds like. So the number of leaf nodes. So in this tree, for example, it would be like 1, 2, 3, 4, 5, 6. So you have 6 leaf nodes in this tree, and that's once again an idea to reduce overfitting.
Yep. We
Uh,
should be using min sample split, right? Yep, that is actually exactly what you should be using. Varun, if you want to go ahead and put the answer into our box there. So looks like Advite used a min sample split of 100 and got a test and trading accuracy both around 0.83. Awesome. I think the min sample split that we used was 200. Let's see what the accuracy and right. So it looks like that one is a little bit worse than the accuracy that Advaith had. So yeah, this is an example of another hyperparameter that can be tuned. Increasing, decreasing your min sample split will change your results, and you can really tune that to your specific data set to try to get the best performance. How does it decide whether it's worth splitting a box into 2 boxes with one higher and one lower Genie impurity? Kyle, I'm kind of confused about your question. Do you want to rephrase that a little bit?
Not sure if that's exactly what you meant, but I'm guessing the question is, suppose you start off with a Gini value. Okay, how does it decide whether it's worth splitting a box into 2 boxes with one higher and one lower Gini impurity? So the idea is that it goes through, so from any node, it looks at a bunch of potential questions. And for each question, it calculates the Gini coefficient of each node, the 2 nodes that it splits into. So like 0.316, 0.38, it's going to do that for 5 or 10 more questions. And then it's going to basically sort of combine the results from the 2 splits and calculate a Gini value again. So for every question, it's going to calculate the Gini values of the 2 nodes here, combine those results and see which one is the best. How exactly it does that, you would probably study that in a more theoretical ML class. It's not particularly complicated, but it would basically be calculating the overall entropy, the overall information gain or the decrease in entropy from asking that particular question, and takes into account both boxes. So there's a preset way in how it determines how it would split 2 boxes. Not sure if that answered your question. Let me know if you have any follow-ups. Okay, cool.
Awesome. Cool. So yeah, Cameron was asking about what is max leaf nodes. So I think that's what we're going into right now. We force the tree to only have a certain amount of leaf nodes. And yeah, so that's exactly what this chunk of code does. So if we run that, we should be able to see. And yep, so I think our what was the number we gave for the max number of leaf nodes here?
5.
Awesome. And if we look all the way at the bottom, we should see 1, 2, 3, 4, 5. So yep, there's 5 leaf nodes right at the bottom. Yeah, so that's exactly what it's doing. And did it print out the accuracy and the accuracy of the train and test? Yep, so it looks like about 81 and 80%. And so it seems like we're hitting a little bit of a wall here with the different approaches we're trying. Seems like we can't break that, 82, 83% accuracy mark. And, sometimes that happens in ML, right? Sometimes you tune your hyperparameters for a lot of different combinations and you're still not able to get the results that you desire, right? So that means you've probably hit some sort of limitation in either A, your model, or B, your data. So if your model is the problem, maybe it's better to try a different model, or maybe continue to iterate over those hyperparameters, try to find something different. And B, if your data is the issue, your options are to A, get more data, get better data, or to maybe add a new feature into your data that you hand engineer. So seems like we've hit a bit of a wall here, and that's about the best we can do. Jacob's asking what ended up being the best sample split. We're actually not sure. We didn't try too many. Besides, we have the answer for 200, and we have the answer for 100 from Advite. If anybody got a better accuracy than the 0.83 that Advite got, please drop it in the chat. Would love to hear it. But I'm honestly not sure what the best sample split is. But I'm sure you can find it out for yourself if you try a few different values. Awesome. So like we're saying, decision tree is probably the most intuitive ML model because all you're doing is you're asking a series of questions till you get to your answer. But there's a way to make decision trees more powerful, and that's if we combine a lot of decision trees together to get a certain prediction or answer. So I'll hand off to Varun now to cover the random forest section.
Cool. Just a recap, in the last couple of workshops, we looked at a lot of models like logistic regression, neural nets, and so on, which at least I felt was a little more fancy than a decision tree, because the decision tree essentially is just asking a series of questions about the data. But the reason decision trees are so important is that unlike a lot of the other machine learning models, you have a very intuitive picture about how it's making decisions about the data. It's not really a black box. And this becomes very important when if you need to explain your machine learning model to someone who doesn't have a very strong technical background. Not everyone spends their time learning about machine learning models. So a decision tree model helps represent how tells the end user how exactly decisions are being made. So in a lot of business use cases, it can be particularly important for communication reasons. And of course, if you combine multiple decision trees, you can actually get really strong results. So let's look at how we can improve decision trees. So before we go into random forest, do you want to take any guesses on how exactly random forest works? It's completely fine if you're way off base. Just curious to see what you guys think random forest could be. You can either unmute yourselves or drop an answer in the chat. Anything works. So we have a couple of answers, lots of random trees and a bunch of decision trees. That is pretty much it. Now let's go into how exactly we would go about creating multiple decision trees. So the idea is that over here, let's say you took a survey of a lot of different people on how they would buy a car, right? Maybe you ask your friend, maybe you ask your uncle, maybe you ask random people you meet on the street, whatever. If you ask a lot of different people about their opinions, you're probably going to get a better idea about what car is best for you. So now what random forest does is essentially it combines a lot of decision trees. Every decision tree is going to make some prediction about a data point, and then your final output is kind of it's kind of like a poll. So if you have 10 decision trees in your random forest and 8 of them say that this person on the Titanic probably survived, then you can be pretty confident that they did in fact survive. The advantage of doing something like this is that when you have multiple decision trees, it significantly reduces the risk of overfitting, because maybe a couple of decision trees in your forest are not really good predictors, but it's highly unlikely that all 10 of them are bad predictors. So you're more likely to learn the overall trend of the data if you use something like random forest. Once again, that's not to say overfitting cannot happen. It's just that it can reduce the risk of overfitting. Right. So we have a really good question in the chat. How does it not generate the same optimal decision tree each time? Does it limit the possible questions differently for each tree when they're generated? So you're exactly right. If you start off with the entire data set, it's going to have the same decision tree every single time. So what we do in random forest is that, let's say you have 10 features, then what the random forest model is going to do is, first it's going to pick any, let's say, 4 arbitrary features from those 10 features randomly selected, and builds a decision tree using just those 4 features. Then maybe a second decision tree will again choose 4 random features, but this time they'll be different. And eventually, when you might also have 2 decision trees that use like maybe a couple of the same features, but you won't have 2 decision trees that use exactly the same features. And eventually, when you have like a forest of 10 to 15 different random trees, each one individually may not have all the features, but combined, your random forest will make use of all the features. And since each tree does not have access to the same features, they'll all be asking different questions. So that's a really good point. If you start off with the same features for every decision tree, you're always going to have the exact same tree for them, and that's not particularly useful. So let's look at this particular image. So here we're basically trying to we're looking at the random forest output for a fruit that has size 5 and is green. Trying to classify which fruit it probably is. So the first decision tree looks at size first, and then looks at size again, and it predicts either cherry, strawberry, or apple. And then you have another decision tree that initially splits on the color and then later on the size. So that's also one thing you can do, where you can switch around the order of the features, or you can use completely different features. It depends on how you choose your data set. Right. And then let's say you had a fruit of size 5 and it was green, right? So this decision tree is going to automatically predict that it was an apple because the size is greater than 3.9. And then the apple is probably not green, assuming it's ripe. You're going to go here. Its size is less than 13.75. So the second decision tree is also going to predict an apple. And since both decision trees tell you that your fruit is an apple, you can be reasonably certain that it is. So like I mentioned before, the more decision trees you have, the more confident you can be about your result. Obviously, there's a balance you need to take. There's no point probably having 1,000 different trees, but luckily scikit-learn will handle the simple cases for us. So the code is exactly the same. If you run this, we see that we have a training accuracy of 98%, which is really high, and we have a testing accuracy of 78%. So what do you think this results suggests? Is our model good? Is our model bad? Do we need to change anything? Feel free to drop any answers in the chat or unmute yourselves. So we have a couple of answers, probably overfitting like before, and that is probably correct. So once again, even though you're using random forest, if you don't optimize the height of every single decision tree, you might still risk overfitting your data. So now let's try to do the same thing, but um, let's restrict some of the hyperparameters. So now we see that while our training accuracy has decreased, we also have an increased test accuracy, and this is similar to what we had before. So just to go over what we changed over here, N estimators is basically the number of decision trees you would use in your model. And max depth equal to 3 simply means that for every decision tree, the maximum depth should be not more than 3. So we just went over a lot of information. So does anyone have any questions at this point? Anything that you feel requires more clarification? Uh, let me know. Uh, so we have a question. How does the program randomize the trees? Uh, so like I mentioned before, uh, it selects a random bunch. Like if you have 10 features, it randomly chooses any 4 features. So that depends on how exactly Python implements randomness. But yeah, it can essentially just pick a bunch of random features and then does exactly what we covered earlier about decision trees. Uh, cool. So we have another question. How do you modify how many features each tree has access to? So that's again another hyperparameter in the random forest classifier. So if you go into the scikit-learn documentation for this, you can play around with the hyperparameters, modify how many features each tree has access to, and so on. So if you look at any of these models in scikit-learn, for example, there will be a ton of hyperparameters. Impossible to remember all of them. For any use case, it's always helpful to explore what those hyperparameters are. Cool. So now what we're going to do here is look at every single tree in our random forest. So this is pretty big, but essentially we had, I think, 4 decision trees, and each of them looks like this.
Yep. I think what's important here is you can see that every single decision tree is different, right? I think that's a point that Varun has been stressing a lot, that every decision tree is different and will split off of different values. And if you take a look at these individual decision trees here, you'll indeed see that that's the case and that they're all different.
Right. And like I mentioned before, what you would do is you'd get a prediction from each decision tree and then try to classify it into the appropriate class depending on a vote. Right. So we covered some of this before. Right. So in the Titanic data set, our first tree could use maybe sex, age, and the number of parents. Another might use the port and the age and so on. And you can play around with the hyperparameters, how many features each decision tree has access to, and so on and so forth. And you can probably come up with a random forest model that gives you a very high training and testing accuracy. So that's pretty much everything we wanted to cover about decision trees. So feel free to play around with the hyperparameters and see what you can do. Um, and keep in mind that if you let your N estimators get too big, so you use too many decision trees, it's going to take a lot of time to run. And similarly, if you have a very high depth, note that at every single stage, the number of nodes pretty much doubles. So if you have your depth set very high, it can once again take a lot of time. So yeah, feel free to play around. Let us know if you come up with a model that does a lot better than ours. We'd be happy to include that in a future workshop. So yeah, that's pretty much all we had to say about decision trees. Uh, in the interest of time, maybe we'll do K nearest neighbors next workshop. So Harsh, is there anything else that you wanted to add?
Yeah, not much else. We figured that it's midterm season, so we'd keep this workshop a little bit shorter. So we're gonna save k nearest neighbors as well as cursive dimensionality and some other cool things. Like different ways to evaluate your models. Beyond accuracy. That's pretty important to see whether or not your model is doing well. We're gonna save all that for next week. We just want to give you guys a little bit more time off, a little more time to yourselves right now because of course midterms are coming up and those are really stressful. So once again, thank you guys so much for coming out to our workshop. In the last code block of the k nearest neighbors little chunk of code, we have our feedback form. We really appreciate all you guys filling out the feedback form for the first 3 weeks. It's been really good to get your guys' feedback and try to tune the workshop every week to try to account for the feedback from last week. And yeah, Varun just dropped the link in the chat. If you guys could maybe just spend a minute or two filling that out for us, that would be really helpful. So yeah, thank you guys so much for coming out. Today was decision trees and random forests, and next week is going to be KNN's cursive dimensionality and different ways to evaluate your classification model. So hopefully we'll see you guys next week. Good luck with your midterms, and if you have any questions, feel free to stick around and just chat with me and Varun. Thanks, guys.
Thank you.
Yep, thank you guys for coming out. Thank you, Jacob. See you next week. All right, Vern, do you want to stop the recording?
Yeah.